And also, where a variable effect in the combination exceeds the effect of the vehicle load, the variable effect replaces this vehicle load, and the one load we use 1.0, one load we use 0.7, temperature weighted effect action we use 0.8, other use 1.0, and the phasor content value of the first and the capacity. So is here the last effect QG for other variable effects in this extensional combination. So this is the second combination, extensional combination. The third combination is the seismic combination. So that's special for seismic. Before we actually this seismic combination belongs to this extensional combination, but now in the new code they just make a special combination for seismic because this is so important, so diverse. So for breeding engineering, the breed capacity, the bearing capacity of the extensional combination of the seismic action and the limit state theory, we use this formula, where M0 is the structural importance factor for the 1.1, 1.0, or 0.9. SGIK is the ice community effect. QIK. Let's see. Which one? QGK. It should be QGK. Maybe this bit. Because in the formula it used QGK. We also here we use QGK. It's a certain magnitude effect of the G's variable effect action that may act simultaneously with the seismic action. So if the implementation to this simultaneously, only this can appear at the same time, you make it into the combination. If they don't appear at the same time, you cannot make it into the combination. So that means when the seismic action appear, and this variable action is also appear. The QC is the seismic effect. Why are there so many things here?
Translation.
Here should be QC. QC is the seismic effect. And here, gamma GI is the permanent action code. Here it go back and use the component coefficient. Just now we use the partial coefficient.
Yeah.
So for this textbook, it's not so.
The translation.
Yeah, translation, because maybe different people translate different parts, so they use different words. Sometimes we confused. So usually, just no matter the component effect or component coefficient or the partial coefficient, the same thing. The specific value are calculated in the character design value code for this bridge. And the relevant combination is just to see some of the code, the Chinese code. And also the same thing is where a variable effect in the combination exceeds the effect of the vehicle load. The same situation as here. And another part of the action effect is for this serviceability action. So this former part, this just now we introduced this combination is for the capacity, loading capacity, bearing capacity state. And now this part is for this serviceability action. Because for the limited state, we got loading capacity limited state and the serviceability limited state. Just now the basic combination, the extension combination, and the seismic combination is all these three combination is used for the design of the loading capacity limited state. Okay, and now for the serviceability limited state, serviceability action effect, we got this different combination. One is the frequency combination, and another one is the pressure permitted combination. So another two combination. Beside this, now we introduce the seismic combination, the exponential combination, and the basic combination. We got another two combination for the serviceability limited state. So the normal use limited state should be these different design requirements using the frequency combination and the pressure permitted combination effect. The effect combination formula is like this. Similar as this, but the symbol inside is different. So where shit missed something? What missed is the effect of SFD. SFD is the effect of design value of the combination of the frequency effect. GIK is the ith permitted standard value. This GIK. For the car load, or vehicle load, including the impact force. Say, here they use the car, for the front part they use the vehicle, so different part they use different words, but the main action is the same. Just because different people translated this. And it is the factor, the value is used 0.7. When the action and the action factor can be considered in a linear relationship, the effect in what's this? Basic value of basic combination can be calculated by adding the action effect. Okay, I feel really bad. With the action and the action effect can be considered in a linear relationship. The effect design value, the effect design value of the basic combination can be calculated by adding the action effect. Okay, this is really bad. The effect design value for the basic combination. Relation.
But in the book is okay?
Yeah, the book is okay. But Just because this electronic one, I just read a picture and scan it, translate it, so make some mistake. But on this book is okay. So another combination is a pixel-permitted combination effect. Pixel-permitted. So frequency combination. So as just now I said, for these two different combinations, which one do you think is the value is larger? This one is larger, or this one is larger?
I suppose
This one.
No, the other.
This one.
Yeah.
No. I said for the first case, we go back to here. Design value, no, here. Which one? Okay, we call this. Yeah, here. Because we said for the variable action, we got a different value. The basic one is the standard value. Besides the standard value, we got a combined value, frequency value, pixel-permitted value. For this frequency value, the meaning is during the design period, suppose 100 years, this value is appears very rare. The value larger than this value, the load value larger than this frequency value appears very rare. So this value actually is a relatively large value. Maybe during this 100 years, the situation larger than this value maybe only 1% or 5%, something like this. Very small chance to appear. So this frequency value actually is a very high level of the variable action. And the pixel-permitted value actually during this 100 years, most of the time the value is larger than this. That means this value actually is relatively at the average level. Because sometimes you see on the bridge, sometimes there's no vehicle, sometimes it's just one or two vehicles, sometimes when it's busy, it's full of vehicle, full of cars. So different situation, the value, the load of the vehicle is different. So this value, maybe you can look at the mean value, maybe suppose 10 cars on the bridge. And most time on the bridge is more than 10 cars. And for this value, you can look at it on the bridge, maybe 100 cars. But most time is less than 100 cars. Maybe just 80 or 90 or 70, something like this. So pixel-permitted value actually is the value appears very often. So that's the pixel-permitted condition. Actually, this two combination formula expression actually very similar.
Yeah.
Just the meaning of the symbol is reflected difference. So here SQD is the effect design value for the that acts as a pixel-permitted combination. So also here miss my symbol. What's this? Is a fair QG here. Fair QG here. Fair QG is the pixel-permitted coefficient of the vehicle. taking 0.4, so the value is smaller. Here we use 0.7, here we use 0.4, so it's relatively smaller. When the action and the action effect can be considered in a linear relationship, the effect of design value SQD of the basic combination can be calculated by adding the action effect. That's 1 plus 1 plus 1. Because it's a linear relationship, if we can read it like this. So finally our book give an example how to do the combination. So this example is simply supported the first computer beam. Bear the self-weight, vehicle action, pedestal action directly. And the standard value of the bending moment at the fourth span and the quarter span for bending moment by self-weight is 512 kilonewton meter, 1 kilometer. And for bending moment by the vehicle action is 245. The impact factor is 1.19. For bending moment by pedestrian action is 3.5. So structural importance factor is 1.0. So it is need to calculate effect combination for the structure design. So if you do this design, what should we do? So first, for the basic combination, used for the loaded characteristic limit state or the ultimate limit state. For this combination, here we got, say, self-weight, vehicle action, and pedestrian action. So relatively simple. In this example, only three, actually one is the permanent action, only two variable action. The vehicle and the pedestrian only got two different variable. So it's pretty simple. And the important factor is gamma 0 is 1, so we just only consider it. So if we do the basic combination, we go back to this combination. Basic combination, see here, in this formula, we gamma 0 now is 1. We don't consider it now. So for the permitted action, only got the self-weight. And for this example is the simply supported beam. Then the self-weight is unfavorable to the structure. So this gamma T I, because only one type of the permitted action, so I is 1. So now we only got the gamma T1. Gamma T1, what's the value is to be? 1.2 or 1.0? 1.2, because it's unfavorable to structure. So another is the Q, gamma Q, because we got the vehicle and the pedestrian. So we see if the vehicle is the mean variable action, normally we use the partial coefficient 1.4, because of course the pedestrian load is smaller than the vehicle load. The vehicle is the mean variable action. So for vehicle we use 1.4. And for the pedestrian, what should we use? Actually, 0.75.
Yeah. Variable action. That is not.
Yeah.
It's
So that means we got this different coefficients for different variable actually. Now we can just use this just use the formula. We can write this. So gamma 0, 1.0, gamma G 1.2, gamma Q Q1 1.4, gamma Q2 0.75. And also, besides this, maybe we have forget another this value. Gamma L G, gamma L.
Gamma Q2 is it 0.74?
75?
75? Is 75?
Yeah. Is this?
Is it gamma or is it few?
5.
5.
Fair. Yeah, here should use gamma. That's
It's not few.
not fair.
It should have been gamma.
Should use the symbol gamma. Gamma, and let me see, another word. How so efficient?
I think maybe it's a mistake.
Hmm?
Maybe it's a mistake.
Which one?
Gamma.
Yeah.
Gamma Q1. Is it here option? This one. The same.
Yeah. So here we got the gamma Q1, gamma Q I, another gamma L G. We need to find gamma L, gamma G, another two coefficients.
We need to find.
Yeah, because see in this formula, beside gamma G, gamma Q, also gamma L, another gamma L.
Yeah.
So let's see if I miss some content here. Gamma,
And gamma actually the hard one too.
yeah,
It's almost the same as the one at the sum after the sum. Gamma LG 1.0.
here we missed something.
Yeah, something's supposed to be there because it's find the item.
I think you see. I think what you miss is gamma. Gamma Q2.
Yeah. It used to be gamma. Or like this one, even the gamma LG, because it said, or after the sentence, then they give the value for the gamma LG. The one on the right side.
Gamma Q, L, let's see, what's this? Yes, the last part. Zero point zero. 4. So actually there's some mistake on this book also. Here, this gamma L, and gamma LG is the coefficient calculated by adding the effect, the H effect actually.
Yoshi. This
Okay.
in this one. This will be the oil. See? Same example. That's what they say.
Yeah.
You should do that, right?
Yeah.
Okay, show you this. I think the gamma keto here. Because this one,
Yeah.
this one
For when I
is
can.
5.
For when I can. Yeah. So this is a different version. In this new version, they use say 3.7 minus 7.
It's 5.
It's fancy. However, the partial coefficient of wind load now is to use 1.1, not this. So it's quite confused to deeply use this value.
It's the same. The here.
No, not the same.
Oh, here.
The first one is 1.4 is the same. 1.4 is no problem. The second one, gamma Q2 is not 1.4. And it should be one, because here, for this example, gamma Q, they also use Q2, yes.
It's 1.4. But I think the difference is this one. Here, they use.
Oh, yes.
Here, but they use.
Yes.
Okay. I think now in the PPT, there is something miss.
Oh, yes, something means yes. Here, my mistake here. Here should be, this should be 1.4 here. And I also got gamma QC. Here is 2.75.
It's a fee. Here it's 5. 5.
Oh, fair, yeah.
Yeah.
What is this on the? Oh yes, it's fancy. Yes, it's fancy. Yes, it's fancy. Yes.
I think it's maybe just the English.
The percentage translation.
Yes, it's very different. Say the old version and the new version. Highway grid and covered. That's code for highway grid and covered.
Residential.
Okay. So now we finished chapter 2, and I think the example for the combination, when you got this textbook, you see this sample, and then you make this value and the class, it's more clear, I think. So now today we finished chapter 2, we continue to chapter 3. So for chapter 3, is nearly talking about the calculation of loading characteristic of flexible member. See, The target is a flexion member. The content is a calculation of the load carrying capacity. So in this chapter, the main content a little bit more content. And this chapter is the most important one. Chapter 3, chapter 4, these two chapters, I think is the most important content. Basic concept of the flexion member and the construction of the flexion member, failure mode, and the mechanical behavior of flow process for flexion member. The basic calculation principle for the loading carrying capacity for the normal section of flexion member. Singly involves the rectangular section flexion member, and doubly involves the flexion member, and T-shaped flexion member. So I think we will finish this class. We have got a design work, design homework or not homework. We have two weeks time for this design work. Maybe we are going to do some T-shaped girl design also.
Okay.
So you see the first part, the report one, basic concept of flexion member. Actually, at the beginning we have taught the flexion member. Will beam or plate bending, the bearing load, they are bending. So at this situation, the lower part is the intention and the upper part is compression. So, and in this structure, only the vertical force has no horizontal force. So this is actually is the flexion member, the situation for the flexion member. So negligible the actual force, the horizontal force. But we said for the arch bridge, because the force is along this direction, so inside the actually got not only vertical and also horizontal force. For the arch bridge and the beam bridge, the biggest difference is the horizontal force. But now we're talking about the flexion member. Here we neglect the actual force. The actual force actually the horizontal force. We only consider the vertical force. So the flexion member is the component that the bending moment and the shear interaction and the negligible the actual force. So the moment and the shear force, all we can see is in the vertical direction. We negligible, how's it word? Negligible. Actually, here we should not use this word. We should use neglecting axial force. So this is some example. The reinforced concrete beam or plate, a typical flexion member in the civil engineering, widely used in the bridge, so small medium bridge or slab bridge structure. So this is a T-shaped beam. 1, 2, 3, 4, 5 T-shaped beam connected together by the horizontal beam of the transverse beam. And this the plate. So this is the three-dimensional model. All this, the beam, the plate actually belongs to the flexion member. So the cross section of the flexion member varies bending moment and shear force. Therefore, the design of flexion member generally should meet the following two requirement. The first one is due to the bending moment, the component. So, what's your question?
Here we are talking about the first concurrent phase or receiving the introduction.
Okay. So, the component may feel along a normal cross section. So this crack is all in the vertical, is normal section, vertical line with orthogonal to the surface in the plane of the beam or plane. Because we know for the beam, not only the vertical crack, sometimes we can see also the oblique crack. So for this bending moment, induce the crack normally is in this vertical direction. So calculation of the loading characteristic of the normal cross section of flex member is needed. So that's for the design of vertical section. And sometimes we also need to design the oblique section, not only the vertical section. You see the failure mode of the normal section. At the bottom, the concrete have generated a large crack. For the reinforced concrete beam, once those cracks appear, normally we just neglect the tensile force bear by the concrete. All the tensile force is transferred to the steel bar. And on the top, concrete was crashed. So once the concrete crashed and the steel bar reached the yield strength, that means this beam, at the limit state is destroyed. And also, we had talked before, if you put too much steel bar inside, when the up part of the concrete was crashed, the steel bar have not reached the yield strength. But at that situation, the beam is also destroyed. But the function of the steel bar have not reached the maximum value. That means you put too much steel inside, you waste the material, waste the steel bar. The best situation is the steel bar reaches the yield strength. The concrete on the top part is a crash. Happen at the same time. So you cannot, if you put too small steel bar inside, the concrete have not been crashed, but the steel bar will break. Reach the yield strength already, so it also break. For this situation, the deformation was developed gradually. You can see the crack was developing gradually. But for that two situation, too much steel or too small steel inside, the destroy happened suddenly. So it's more dangerous. So that means you should properly design your beam. That means too much steel. Too much steel doesn't mean this structure is safe. Because lots of people, if they don't know, they may think I put a more steel bar inside, maybe this structure more stronger, but that's not true. Maybe it's more dangerous.
No.
So Alaushi, the best way is to do well the calculation. The best way to do is to calculate well.
Yeah.
The calculation.
Yeah.
Puts the same.
You should control the reinforcement ratio. That means the steel bar inside the concrete. have control this in a proper how to say the proportion. Yeah, not too much, not too small. And the second situation is under bending moment and shear force, a membrane may fail along the inclined cross section like this. Not only the vertical crack, also the inclined crack may also fail at this position, not necessarily here. So, along the radius is shear compressing the vertical line or the surface with the oblique plane. The collecting the loading capacity of the or oblique section is needed. The failure mode is like this. With this beam destroyed, it's broken from here, not in the middle. It also will happen like this. So that means if the shear force is too large, maybe you are broken at this position. If the moment is too large, maybe broken in the middle. If the shear force is too large, it's broken at here. In this inclined section. So this chapter focuses on calculating the loading characteristic of the normal cross section.
On the previous slide. So you're saying if the moment is high, then the crack generated at the top part will be in the middle.
Yeah, if the moment is too high, the most dangerous position may be in here, because we know for the simply supported beam, the moment is from the support bearing support to the middle side increase greatly. But the shear force, the biggest shear force actually is in here. See, the shear force is at the bearing support position is the largest. So if from here you see, when the moment is large, the dangerous position is here in the middle. If the shear force is too large, the dangerous position is like here near the supporting bearing support position. So here, for the moment too large, it's broken like this. For the shear force is too large, it's broken like this.
Down.
But in this chapter, we mainly focus on the normal cross section. That means in the middle design of the normal section. Chapter 4, we focus on the inclined section. So this aim is to define and design the area and the longitudinal steel reinforcement or the reinforced concrete beam and the plate. Is the design value M. So you have to design calculation how much is steel you should put inside and which position at the bottom or the top. Yeah, because we said we got it here at the beginning. We said we got single reinforced, double reinforced. Single reinforced for this rectangular section, normally the steel bar is thin on the bottom. Double reinforcement means sometimes we also put the steel bar on top. Because for the continuous beam, continuous bridge, normally in the middle, the moment is a positive moment, but for this is a simply supported beam. But for this continuous bridge, the moment is like this. And in the middle supporting point, the negative moment is also very large. That means at this position, you need steel bar on the top to bear the negative moment. So some situation which we need to do this double reinforced.
Okay.
So the second part, 3.2, some of the requirements for the construction and the design, construction and shape of the cross section for the flex member. Construction requirement. What's the construction requirement? It's based on specification or less learned from the project. Yeah, from the real project. Some of these restriction on the component size and the material strength. That means for special position, your structure, the size of the section, you cannot too small or too large, something like this. Most based on the real project lessons. And so the material strength, grade, variety, steel quality, layout, location, space, diameter, something like this. Because I'll say for some of the reinforcement skeleton, you see find some picture. So you see this picture, the dimension between the two scale bar, the requirement for this dimension, they have got a requirement. Normally not less than 10 centimeter or something like this. So that requirement belongs to the construction requirement. Because if this dimension is too small, when you pull the concrete inside, it becomes difficult. And also, if you use the shear machine to, you make the concrete uniform. What you call it? You see, when you put the concrete inside, you need to shear machine. What's it? 振动。Bomb, what's this? Vibrator. Is this? Concrete vibrator, yeah. Sometimes it's very, if this dimension is too small, you cannot even put the vibrator inside. Yeah, this situation happened. Some designer make this design very close to maybe just 2 centimeter or 3 centimeter. It's too small. You cannot put the vibrator inside. So for the construction, it's not possible. So that's some of the construction requirements, not related to the calculation. Just because for the construction, you should, besides the calculation, you satisfy the loading capacity, and also you should satisfy the construction requirement. Make it possible to construct it. And the structure design involves many problems. Some problems are non-essentially, but cannot be ignored. And some problems have not yet been figured out and cannot be solved with the computation theory and quantitative command. So all the problems that cannot be reflected by the design formula and identified quantitatively. According to engineering experience and scientific research, considering the possibility of the construction as well as the requirement of the technical and economic, they summarized here. The first part is to offset the theoretical disadvantage and the effect of the uncertain factor. That means because some of the theory or formula actually is come from the experience or experiment. It's not exactly correct. should make some requirement to make sure it's have some space to make it more safety. So offset the theory disadvantage. And the construction requirement, such as the requirement of medium thickness of the plate, thickness with or thickness the cover thickness. Some of the plate, you cannot make this too thin. You have, for the real situation, at least you have make sure you have enough cover thickness to protect the reinforcement inside. The engineering experience, such as spacing with distribution reinforcement, just now I said, if the spacing is too small, it's not possible to so that's the engineering experience. And the other technical and economic requirements, such as material, construction, something like this. So that means the construction requirement actually most is because the lesson from the project, real project, and some is for the how to say perfect of the theory, because for the civil engineering there's no exactly perfect theory or formula for the calculation, especially some very completed structure or situation. You should make sure they have space, some of the safety space to make the structure safe. The role of the construction requirement to structure design is to provide a reference for preliminary styles of the component. Something like the H divided by L, the span, L is span, H is the height, like the beam. We do suppose ask you to design a simulation for the beam. Maybe the span is 40 meters long. So when we design, how the height of the beam, how you check, how much you use, 4 meters, 5 meters, 6 meters, something like this. So if the span is fixed, the height of the beam, they have a scope for design. Actually, it's based on the experience. Something like this, 1 divided by 10 to 1 divided by 18, something like this. Because for the value in this scope is more economic and I'll say the safety, something like this. Maybe if you don't use this value, if 1 divided by 9 or 1 divided by 20, you also can make a finish the design, but the design maybe is not very good. Maybe it's you wasted too much material, or it's not so safety, something like this. And the second part is to be complementary with the computational, because the theory or the formula is not so perfect. And to select the fracture of the actual project design, something like this. Some of the second part, the size, is to project this rectangular T-shaped box girder and this plate, the plate and the empty hole inside. This was the first line, integrated plate. The second, assembled plate, referring to the hollow decks. In the real situation for the bridge, normally it's those sections. Or sometimes maybe the section like this. Or this is the
TV.
not TV, just I, just like I mean, but not much. For the steel structure, sometimes we use this type. The second type of the reinforced concrete beam is slab. This mainly this three types: the integrated, the assembled, and the prefabricated hollow decks. And for the beam section, such as the rectangular T-shape, R-shape, box shape, and the inverted T-shape. Inverted T-shape is not used often.
Okay.
The type of the base section, such as the flat roof, porous plate, this is most used, just like this. And some of the size requirements. The size requirement of the slab. Integrated casting side slab, section-wise, is large, but a unit-wise, for example, 1 meter for the unit, for the rectangular cross-section used for calculation. When you design, when you calculate, normally we use 1 meter wide plate calculation, because this is an integrated casting side slab. Maybe the slab is 10 meters wide, you just cast inside the one time to make it. But when you calculate it, normally we don't just make the model 10 meters wide, we just build the 1 meter wide model calculation. For the prefabricated slab was control the 1 meter to 1.5 meters in order to meet the requirement of the transportation and hosting. And the construction conditions are perfect or good. Not only rectangular solid plate is used, but also more complex shapes with the rectangular cross section, hollow plate, plate are used. Slab thickness H is controlled by the largest bending moment in control cross section, and the bending stiffness of the slab, and need to meet the construction requirement slab. So what's the mean? The thickness of the H is
Largest bending.
thickness of H is controlled by the bending moment. So the thickness you cannot too small or too large, because the plate is bearing some moment. Usually it's determined by the calculation. And in this code, provide the medium thickness of variety slabs. For the sidewalk slab, integrated casting side is not less than 20 millimeters, 8 centimeters. 80 centimeter, 80 millimeter. Right. For the sidewalk precast, 6 millimeter. Top and bottom slab thickness for the column is not less than 80 millimeter. So this way, different code maybe have different requirements. Because of the material. For the concrete and steel, everything inside a rectangular beam. This is the size for the requirement for the beam. This part is for the slab. So slab and beam is different. So for the beam, what was cast inside the rectangular beam is often taken as 120, 150. 120, 150, like this. Beam was increased 50 millimeter. When the beam height smaller than 800 millimeter, they increase by 100 millimeters. The ratio of heat to watts with the rectangular beam is generally taken as 2.245. And for the prefabricated span, we normally call it highest span ratio. It's generally defined as 1 divided by 11 to 1 divided by 16, something like this. And a larger span often has a smaller value. What was B or being read is often taken to be this value, 15 to 18 centimeter. It's not a reinforcement arrangement and a shear requirement. The thickness of T-shape cantilever beam and flange beam and flange not less than
100 millimeters.
1 meter, and the thickness beam is not less than 10% of the beam height. So, yeah, there's a lot of those things.
She's over.
It's over.